Hello everyone, welcome to my video on understanding the Hopcroft Karp algorithm for finding the maximum matching in bipartite graphs. In this video, we will learn about bipartite graphs and explore how the Hopcroft Karp algorithm efficiently solves the maximum matching problems. Let us first know about what are the bipartite graphs. Bipartite graphs are the graphs whose vertices can be divided into two disjoint sets such that no edges exist between vertices within the same set. They are often represented as x, y, where x and y are two disjoint sets of vertices. Bipartite graphs have various applications in areas such as social networking, social networks, matching problems, and resource allocation. Here is an example of bipartite graph and complete bipartite graph. A bipartite graph contains vertices. These vertices are divided into two disjoint sets. For example, set A and set B, which are circled on the edges in a bipartite graph. Each edge is a possible match between two vertices. However, an edge cannot match two vertices that are on the same set, like this. Let us know about what is matching. As shown in the example, a matching is a set of edges without common vertices. In the following graphs, the matching will be shown by black edges. In this second bipartite graph, we have two vertices matched to the same vertex, thus having a common matched vertex. So we can say that this graph is not matching. Finally, in the third example, we have a maximum matching. This is what we aim to find using Hopcroft Karp algorithm. Maximum matching problem. The maximum matching problem involves finding the maximum number of edges that can be drawn in a graph without any vertex being incident to more than one edge. It is a fundamental problem in graph theory, with applications in network flow scheduling and matching algorithms. Let us know about augmenting paths. Augmenting paths starts at an unmatched vertex and ends at an unmatched vertex. And the edges in the path alternate between being in the matching and not being in the matching. Let us see about Hopcroft Karp algorithm. The Hopcroft Karp algorithm is an efficient method for finding maximum matching in bipartite graphs. It was proposed by John Hopcroft and Richard Karp in 1973 and is based on augmenting paths. The algorithm offers a time complexity of big O of root V into E, makes it suitable for large graphs. Let us see the algorithm. Let's dive into the BFS phase first. This is where the algorithm traverses the bipartite graph layer by layer, searching for augmenting paths. Think of it as exploring the graph horizontally, one level at a time, to find the paths that can increase the matching size. Once a BFS phase identifies potential augmenting paths, the algorithm switches to DFS phase to validate and update the matching. DFS explores the graph more deeply, finding alternate paths and adjusting the matching accordingly. The algorithm continues alternating between BFS and DFS until no more augmenting paths can be found. At this point, it terminates and the current matching is deemed to be a maximum matching for the bipartite graph. Let us see the time complexity. The time complexity of Hopcroft Karp algorithm is big O of root V into E, where V is the number of vertices and E is the number of edges. The algorithm's efficiency makes it suitable for solving maximum matching problems in large bipartite graphs. In the best case scenario, the algorithm may terminate after a small number of iterations. This occurs when the maximum matching is found quickly. The best case time complexity of the algorithm is big O of root V into E. The average case time complexity depends on the structure of the graphs and the distributions of edges. And the worst case time complexity of the Hopcroft Karp algorithm is big O of root V into E. However, in the worst case scenario, the algorithm may need to iterate big O of root V times, each time performing a BFS and DFS, resulting in the total time complexity of big O of root V into E. Here is the C++ implementation of the algorithm. Let us see an example. Here we are taken an example for linking people to different tasks that need to be done for preparation of some festival. So on the bottom of the bottom left, we can see list of people which are assigned with different tasks. In the middle, I got the bipartial graph, which is showing all the possible edges linking a person to the task they could be doing. So let's move on to the first step. So the first step was to initialize the current matching to be empty. So the first step was to initialize the current matching to be empty. So I done that. You can see there are no edges in the current matching. Now the next step was to start using breadth first search to build an alternate level graph rooted at unmatched vertices. After the first iteration, I got this matching here and I highlighted the vertices which are unmatched in yellow color. Next, we have to get the unmatched vertices on the left side of set A and we put them at the top of our alternate level graph. Now we need to look in our graph and table and see what are the edges that are not in the matching go from these vertices. So if I look into the table for loop, I got an edge to 7 and an edge to 2. So I add those to my graph. And for R, I got an edge to 6 and another edge to 7. So I added them into my graph. Now on the right side of the graph, we got to put the edges into our graph that are in the matching. Now, if we look at our bipartial graph, we can see there is an edge from 2 to J and 7 to E and 6 to T. Then we move back over to the left and we going to look for the edges that are not in the current matching that go from J. We not included 2 because that is in the current matching. And we can also see J to 5, J to 4 here and E23 and E26 and T27 and T25. Now we are going to stop here. As you can see, we are reached our unmatched vertices. Because of that, we are stopping our BFS here. Now we move on to our next part of the loop, which is to augment the current matching M with a maximal set of vertex disjoint shortest length paths. Now let us take number 4, and here by using DFS we are going to get to the unmatched vertex on the other side. So either L or R, we are going down this tree. Now using this path from 4 to J and J to 2 and 2 to L, using this path we reached L. So to make sure that this path does not appear in another vertex, we need to remove this path. Now from 5 we are using another path 5 to T and T to 6 and 6 to R. By using this path we reached to the unmatched vertex R on the other side. After that you can see there are no unmatched vertices for us to go. So we finished this part of the algorithm there. Now we can see we got 4 to J, 2 to L and 5 to T and 6 to R. So I changed the edges as we get, and here we got every vertex is matched with another vertex from other side, and no vertex is matched with the same vertex on the vertex on same side. So we got our maximum matching vertex as 7. Yeah, C++ code which I mentioned earlier, and this is the .csv file from which we are taking the inputs. Let's run the code. It's asking the file name. Let's give the file name. Here you can see that we get the output as 7. We implemented the Hopcroft Karp algorithm in C++ for finding maximum matching by partial graphs. The code reads a graph data from a file and outputs the size of the maximum matching. The Hopcroft Karp algorithm has various applications in real-world scenarios, including job assignment, resource allocation, and network flow optimization. Its efficiency and versatility makes it a valuable tool in solving matching problems in diverse domains. Conclusion. In conclusion, the Hopcroft Karp algorithm provides an efficient solution for finding the maximum matching by partial graphs. Its time complexity and effectiveness makes it a preferred choice for solving matching problems in various applications. Thank you.